Let's just quickly recap the subgradient method and then go to a few applications of the subgradient method, or maybe one important application in particular, which is the alternating projections method. Talk about stochastic subgradient method, and then move on to proximal gradient. So last time we talked about a problem where we're minimizing a function that's convex, that is a full domain, but it's not necessarily differentiable. So something like gradient descent would not apply, and we learned that essentially, if it's replaced gradients with subgradients, then that method will work as long as we kind of keep track of the best criterion value we've seen so far. So this method is called the subgradient method. Just repeatedly evaluate a subgradient of our criterion at the current point. That's called gk minus 1. And we update in the direction opposite to that subgradient, where this tk is the step size. Okay. And we saw that it wasn't necessarily a descent method. We saw it through an example in which the criterion kind of bounced up and down as we proceed. So what we typically do is just record the iterate that had the best criterion value so far. And if we had to stop after, say, 5,000 iterations, then this is the iterate that we'd end up with, the one that had the best criterion value so far, not necessarily the last one. Okay, we saw a bunch of stuff. Just to remind you, the step sizes of a subgradient method are typically chosen to be either fixed or diminishing. There's not really a general analogy to something like backtracking line search. And the convergence analysis is quite different. It led us to the conclusion that the subgradient method converges at the rate 1 over epsilon squared to get an epsilon suboptimal solution, compared to gradient descent, which had a convergence rate of 1 over epsilon to get an epsilon suboptimal solution. Okay, so it was quite a bit slower in that regard. And we saw that through an example as well. Okay. The last thing we talked about was a different choice of step size called the Polyak step size, which rely on knowledge of the optimal criterion value, f star. And in most examples, you may think that that's not something that's necessarily known, although it is actually known in some examples. And we're going to show you an application of the Polyak step size, an application that uses Polyak step sizes next. But if we happen to know f star, then we could take as our step size the suboptimality gap at the current point, xk minus 1. So this is f of xk minus 1 minus f star, divided by the norm of the subgradient, okay, at xk minus 1 squared. And this is motivated by saying that if we were to go back and see how the subgradient method was analyzed, how we derived its convergence rate, for example, then this gave us kind of the tightest upper bound possible in the first gradient, in the first step of the subgradient proof. Okay, so this somehow is, you can think of it as having some mathematical justification. And with this step size, we still know that even though it's changing over the course of the algorithm, and it's being affected by somehow the norm of the subgradients, it still gives us a convergence rate of 1 over epsilon squared. Okay, so it's really, in a sense, in terms of rate, still no better than what we were doing with a carefully chosen fixed step size to get an epsilon suboptimal solution. Question?
So what goes wrong if you choose, if you have a Rothius of, say, f star?
Yeah, that's a good question. So if you don't know f star, then you can estimate f star. I'm trying to see if I can remember how that's done. So I would want to avoid kind of giving a specific formulation for how people estimate f star, because I don't remember the details and I don't want to get it wrong for you. But there are ways to use something like this where f star is estimated, and you can still prove that it converges, and it still is the same rate. You have to just make sure you're estimating f star carefully. Good question. Other questions? Okay. So let's look at an example in which these are useful. These Polyak step sizes are useful, and it's a pretty simple problem. It's kind of a classic problem. The problem is that you're given a collection of closed convex sets. Let's call them C1 through Cm, and I want to find a point in their intersection. Okay, and let's call that point x star. So we can actually formulate such a task using a convex optimization problem, and we're going to just define a bunch of functions to get us started. For each I, we're going to define the distance function between the set Ci and a point x. This is a function of x as fi of x. Okay, remember we saw that in the last lecture on subgradients. We actually computed subgradients of this thing. Okay, we showed that there was a subgradient that was very natural, and in fact, it was the unique subgradient if you're at a point that has a positive distance to the set. Although we didn't prove uniqueness, we at least proved that through kind of some simple geometric calculations that if you take x minus its projection onto the set Ci and normalize that, then that's a valid subgradient to the distance function. Okay, so this guy is convex, gives us a distance between, draw you a picture. This is Ci. This distance function gives you this distance, the distance between any point x and Ci. And we're going to define f of x to be the maximum of these m functions, fi of x. Okay, so it's the maximum distance of x to any of the sets in our collection, C1 through Cm. Okay, so let's suppose this was Ci and this was Cj. Then the distance function for Cj is this one, distance function for Ci is that one, and f of x is the maximum of these two. Okay, and so far as I drew it, it looks actually like they're probably about the same. So now we're gonna think about solving this problem. Minimize all x the function f of x, and if the optimal value is 0, right, then we have a point x star, the guy that minimizes this. It's not necessarily going to be unique unless somehow these things only intersect at a singleton. But if we ever find a point x star that has optimal value, f star equals 0, then we have a point in the intersection. Okay, and likewise, if we know that, for example, these sets should have a non-empty intersection, we just, we don't have a point yet that we've considered in their intersection, but we know that they actually do have a non-empty intersection. Ahead of time, that f star is 0. Okay, so this is an example of a problem in which, we may write down some sets that we know somehow have a non-empty intersection. So we know that f star is 0. The optimal criterion value for this problem is 0. But now we want to go through the task of constructing a point in the intersection. We actually want to arrive at a point x star in the intersection. Okay, so we're going to think about running the subgradient method on this criterion, knowing this is the optimal criterion value, and using the Poliak step sizes and see where that takes us. Okay, that's the setup. So this is the distance function, right? Let's just fix an arbitrary set C. Recall that the distance between x and C is defined as the minimum, let's say, 2 norm between any point y in the set C and x. And last time we showed that actually we phrased this in terms of subgradients, but if you remember that when the subdifferential has a unique element that gives you the gradient for a convex function, you can think about our result from last time telling us that as long as you're at a point x whose distance to the set C is positive, this distance function is differentiable, and its gradient is nothing more than x minus the projection onto the set C normalized, divided by its norm. Okay, so that is what we proved last time. P of x being the projection onto the set C. So this being, for example, PCI of x, and this thing being PCJ of x. Okay, they're projections onto the sets. And also remember, we had this rule for subgradients of maxima of functions, of convex functions, right? If you have a bunch of convex functions, let's say f1 through fm, you take their pointwise max, then what's the subgradient of that? Well, we learned last time that you look at all functions that achieve the max, take their subdifferentials, take the union, and take the convex hull. That describes all the subgradients of f, which is the pointwise max. Okay, so that was our rule for subgradients of maxima of functions. So what we can say, suppose we just wanted a subgradient, a valid subgradient at the point x of the function f, then we can say from this rule that if you happened to find a function that achieved the max, right, if fi of x was equal to f of x, and you grabbed a subgradient from that function at x, so I took a gi in the subdifferential of fi at x, then that is certainly going to be a valid subgradient for f at x, right? Because it's an element of the subdifferential here, and the subdifferential for f contains that and more, possibly much more if there are many functions that achieve the max. But this is still certainly going to be a valid subgradient. Okay? So find the function that achieves the max, take a subgradient of it. That'll be a valid subgradient for f at the point x. So that's kind of what we know from our knowledge of the calculus of subgradients. So let's put these two facts together for our current problem in the context of our intersection of segs problem. Then by saying that fi achieves the max at the point x, we're saying that actually x is farthest from the set Ci, right? Or at least it's tied for the farthest. So let's just draw an obvious example. Let's suppose that somehow this was, well, not a great example because they don't have a common intersection, but still. Let's suppose this was CL, the set CL. Then this will be the function that achieves the max, this guy, FL. Because this is FL of x, right? This distance, this is Fj of x, this is Fi of x, and this one achieves the max. In other words, x is farthest from the set CL compared to all the other sets in my collection, at least in this picture. So we grab a subgradient of its distance function, right? But remember that all these functions are actually differentiable, so and they're convex, so their subgradients are just their gradients, which means that gi is nothing more than what we saw already, right? X minus the projection of x onto Ci normalized. And that serves as a valid subgradient to our full criterion. Okay? This picture is not great because these three sets don't have a common intersection, but if I keep these sets convex and just try to make Ci large, then maybe they do now. Okay, maybe the intersection is down here or something. Okay. This is not a great picture for the example, but I'm just trying to demonstrate for you the various distances. Okay, so we're going to think about applying the subgradient method now with the Pollyak step sizes. Okay, and think of what happens at an arbitrary iteration, let's say k. So we take the point that we're currently at, xk minus 1, and we subtract off, right, tk times the gradient of our criterion function at xk minus 1. Okay, well, that's the gradient of our criterion function at xk minus 1 if Ci is the set that's farthest away. That's what we just proved is a valid subgradient, right? So this thing is a valid subgradient of our criterion if Ci is the set that's farthest away. And we're going to multiply by the Pollyak step size, but if we go back to what that was, okay, f star is 0, so it's nothing more than the value of the criterion xk minus 1 divided by the norm of the subgradient squared. But look, this guy has norm 1. Okay, so it's nothing more than just the value of the criterion xk minus 1. That's what the Pollyak step size instructs us to do in this case. Okay, and let's just rearrange this, right, to find out that, well, if Ci was farthest away from xk minus 1, right, then our criterion value at xk minus 1 is, which remember it's the distance, it's the, well, yeah, it's the maximum distance from xk minus 1 to all the sets. It's equally well the distance from xk minus 1 to Ci, right, because it's the farthest away. That's how we defined it. And that is nothing else than xk minus 1 minus the projection of xk minus 1 onto the set Ci. Take the 2 norm of that difference. Okay, that's just the definition of the distance function. So in other words, if Ci is the set that's farthest away from xk minus 1, the criterion value is exactly this quantity, the 2 norm of the difference between xk minus 1 and its projection onto Ci. So if we look at the the subgradient update, what would that be? It's of this form. Right, that's the Pollyak step size. And here is the valid subgradient of our criterion. It's this guy divided by its 2 norm. And you can see what happens is these things cancel, right? These are the same. So the subgradient update is nothing more than just right, xk minus 1 minus the quantity xk minus 1 minus its projection onto the set Ci. So it just becomes the projection of xk minus 1 onto the set Ci. So this is the subgradient update. In other words, we just identify the set that's farthest away from our point xk minus 1, and then the next step in the subgradient method is just to project our current point onto that set. So we find the set that's currently farthest away, right, from our point x, and then we move ourselves basically to lie on the boundary of that set by projecting x onto that set. And then it looks like after that, say this set is going to be the farthest away, so we move ourselves by projecting ourselves onto that one. Okay, so we repeatedly project ourselves onto the set that's farthest away from where we are currently, and we'll end up eventually at a point that's in the intersection of all of our sets. Okay, so it's the well-known kind of alternating projections algorithm. In a special case of this, just with two sets, for example, is that we're just repeatedly projecting onto the other set, right? Because as soon as you project onto a set C1, then your distance to C1 is 0, and set C2 is the farthest set away. So with two sets, it's just alternating projections. With more than two sets, it's always projecting to the farthest away set. Okay, so it's a very natural algorithm. I think that, certainly had you been given two sets, you may have just thought of this algorithm kind of on first principles. And it has a nice history associated with it. People have studied this alternating projections algorithm I think through several different lenses before. But what's interesting, though, is that we actually have derived this as a special case of the subgradient method, right? With this particular choice of step size, the Pollyak step size, and this particular criterion, which means that we can say that actually this algorithm converges, right? First of all, we know that it converges, right, for arbitrary configurations of sets, which is kind of a nice result. We didn't have to somehow analyze specifically what happens geometrically with this type of algorithm. We also know how fast it converges. It converges at the rate 1 over epsilon squared. Okay, so if you want to get a point that's within epsilon of every set in your collection in terms of its distance, then you need on the order of 1 over epsilon squared iterations, or projections in this case. Okay? Any questions about that example? Yeah? Right. So this is a question I think maybe every year I've taught this, I've gotten that question. It's a good question. It doesn't necessarily give you a point in the set, right? Because if we stop at some point when we're epsilon suboptimal, then you're epsilon away from every set. So how do you deal with that? Well, there's one kind of cheap way to deal with that, which is you just inflate all the sets. So add a little kind of tube to all the sets. And if your sets are defined by inequalities, that's usually easy to do. Right? If I have something like this, if Ci was, for example, the set of all x for which, let's say, f of x was, or I should use a different function. Let's say gi of x was less than or equal to ti. Then I can think about maybe taking, before I run this method, a slightly larger set, something like this. Okay, and then I'll if I get close to this set, then I'll hopefully end up in this set. Good question. Other questions? Yeah.
So what happens if there is no intersection of all?
Right. So let's first ask ourselves what the optimal value would be for this criterion. It would not necessarily be 0. If there's no intersection, so I guess from what we know about the subgradient method, I would think that this doesn't necessarily converge. Although this algorithm, the steps still lead us to this alternating projections, right, or this repeated projections. Nothing here that we've used so far uses the fact they have a common intersection. These are just outlining the steps of the subgradient method. Although I think you probably could construct an example where this would fail, right? Okay, so here's a kind of perhaps obvious example, right? Something like this, I would just alternately project between these two sets back and forth. Yeah, so you're saying it would still solve this, it would still minimize this criterion, but it wouldn't give us a point in the intersection of sets. Yeah, I guess it's an interesting question. Yeah, I don't really know whether or not this kind of step size is always guaranteed to minimize this problem for this particular setup. I mean, it's a good point. Just point out that, this is an example where the subgradient method doesn't converge in terms of iterates, right? It's just going to cycle back and forth, but it does hit the minimum criterion value. Probably boundedness would be important here too. If somehow we can cycle in such a way that the criterion value stayed the same, but the iterates grew unbounded, then I guess you might be able to break it. But still a good question, yeah.
In the previous example where you wanted to check whether it's in the set or not, you said you want to inflate the set or you want to deflate the set?
The previous example was just this one, you mean?
Yeah, you want to inflate it in the set because then you might, when you inflate the set back, you might be in the set.
Yeah, that's a good point. Thank you. That's just a typo. So if you take your sets to be smaller, right? So if this is Ci, if I defined C tilde I to be something that's smaller, right, then getting close to Ci would put me inside Ci. Getting close to C tilde I would put me inside Ci. Thank you for catching that, yeah. So, and I guess in this example, you take something, you take a little smaller constraint rather than a little bigger. Okay, all good questions, or good points. So, in the subgradient method, and then we'll move ahead to proximal gradient. To minimize a convex function that's not necessarily smooth over a convex set, we can use something called the projected subgradient method, which is just like the usual subgradient method, except for after we take this kind of usual subgradient looking update, we have to project ourselves back onto the set C, right? Because this step would not necessarily be feasible. If we're at xk minus 1 and we're in the set C, right, because we're maintaining a feasible point so far in our subgradient method, then by taking a step opposite to the subgradient, right, times the step size, this may actually put us outside of the constraint set C we had in our original formulation, so we need to project ourselves back onto the set C. So this is something called the projected subgradient method. It's analyzed very similar to what we have already done, or I guess I didn't really go through many of the details of the analysis, but the analysis for this is very similar to what's in the slides. For the usual subgradient method without constraints, you get the same kind of convergence guarantees under the same types of step sizes and the same convergence rate as well. Okay, so it's just a generalization of the subgradient method to handle constraints. It's worth taking a second just to ask ourselves, when is this going to be useful, right? Because we already saw that somehow I could write any convex problem, any convex problem in existence in this formulation. Minimize some function that's convex, subject to a convex constraint on my variable x. So if this algorithm now worked generically, we'd have an algorithm that works for all convex problems. So in principle, this does, but it's this projection step that is usually hard. I mean, computing subgradients can be tough, but I think it's really the projection step that usually is the real bottleneck if you start talking about kind of very generic-looking problems, because projections onto convex sets are not always easy to do in practice. So I just made a list here of some sets that are actually quite easy to project onto. For each of these, we either have a closed form expression for what the projection looks like, or an algorithm for finding the projection in, let's say, efficiently and close to linear time or linear time. So here are some of the examples. An affine image is an easy set to project onto. For example, the set of all ax plus b as x varies. This is something that's in the column space of a matrix A plus a shift. Okay, it's quite easy to project onto this. Same is a solution set to a linear system. A set of all x for which, let's say, ax equals b for a matrix A in vector b. Okay, with this thing really only being interesting when A is rank deficient, so that this this is not just a singleton. There are being many solutions to this linear system. So as an exercise, I would say see if you can derive the projection operators for these two types of sets. Okay, they're going to involve just kind of simple. It's a simple problem. You can kind of do it in linear algebra to see whether you can write down the projections onto a set of this form or of this form. Non-negative orthant is a very easy set to project onto, right? I just, if you give me any vector and I want to see what's the closest vector with all positive components to the vector that you gave me, then I just look at each component and I either keep it or I set it to 0 if it happens to be negative, right? Just basically apply the positive part to every component of my vector. Norm balls are often easy to project onto. For example, you guys know already how to project onto the 2-norm ball, right? Which is just take the vector you're given and normalize it. That's going to be the closest vector in 2-norm to the 2-norm ball. That's the closest vector in the 2-norm ball to any given vector. And it's also possible to do when the norm here is not just the L2 norm, but say the L1 norm or the infinity norm. Those are easy sets to project onto as well. The 1 norm being the trickiest. Okay? The infinity norm is actually also quite easy. That's just a projection onto a box. So I'll let you think about that. And the 1 norm, like I said, that's one's actually somehow the trickiest, although we still can do that efficiently. If this is an n-dimensional 1-norm ball, we can still do that with order n operations. And there are a bunch of simple kind of polyhedra and simple cones that we can also write out some projections for. So there's a bunch, but an important warning is that it's actually quite easy to write down a set C that looks simple, whose associated projection operator is very complicated. So a good example is an arbitrary polyhedron. So if you just give me an arbitrary matrix A and vector B, projection onto this set is not easy. Okay, there's not somehow like a linear time algorithm for this. This is itself an optimization problem. And this would be actually a QP if we wrote this down. It's not very easy to solve at all. So basically, if you're going to be thinking about projected subgradient or doing projections, then you should be kind of careful, or at least cognizant of the set C. Is the projection operator for that C something that's kind of simple or known or tractable? Projected gradient descent also works just like projected subgradient method. And in fact, we'll just see that as a special case of proximal gradient, which we'll discuss in a few minutes. Okay. Okay, so the last bit I want to talk about for the subgradient method was stochastic subgradient method. I guess I called it stochastic subgradient method. And we want to minimize here, let's say, a sum of functions fi of x, which we're thinking about the sum as being kind of over many functions. So we have a lot of functions in our collection, and we're minimizing their sum. So stochastic gradient descent, remember, basically picked out one of these functions either at random or cyclically in order, one at a time, and evaluated the gradient just of that function and allowed that to dictate our update direction, right? Move in the direction of the negative gradient of just one of these things, rather than the sum of the gradients, right? That sum being a lot more expensive to compute. So stochastic subgradient method is similar. We just replace gradients by subgradients. So at each step, we just choose some index, either randomly or in a kind of cyclic fashion, moving through this set one at a time and repeating. And we just evaluate the subgradient of, say, the function fik, rather than all of our functions, and just take its subgradient at the point xk minus 1 and move in the direction opposite to that, rather than what the usual subgradient method would do, which is take a sum of all the subgradients of our functions, right? Because it would take the subgradient of our criterion, and from our rules on subgradients, right? Subgradients for a sum of convex functions, we can just take a sum of subgradients. So that would be the direction used by the, opposite to this would be the direction used by the usual subgradient method, and then stochastic subgradient uses just subgradients from one of the function at a time. Okay, and when these functions are differentiable, this reduces to what we already saw with stochastic gradient, or SGD. So now that we've learned a bit about rates for the subgradient method, we can say something a bit more precise about what happens with these stochastic methods. And our setting for that is going to be that we're going to assume that each one of these functions is itself convex in Lipschitz with a constant g. So just for simplicity, I've kept the Lipschitz constant for all of these functions the same. could be different in practice. So you could take g to be the biggest of all the Lipschitz constants if you wanted to kind of handle a situation in which they're all different, or you could make more refined statements if the Lipschitz constants were very different. But just for simplicity here, I've just said let's just assume that they're convex in Lipschitz with the same Lipschitz constant. So we're going to think about taking fixed step sizes. Okay, each one of these step sizes tk being set equal to t, and think about either running the cyclic or randomized rules for the stochastic subgradient method. And they both satisfy the following kind of suboptimality bound, which is that in the limit as we take more and more steps with stochastic subgradient method and fixed step sizes, the best criterion value we see is something like the optimal criterion value plus 5 times m squared g squared t over 2. So let's just go back really quickly to what we saw for subgradient method itself. It's a very similar looking bound, right? The only difference I claim is actually just the 5. So here we saw with subgradient method, after, if we take a fixed step size t and we let this run forever, then the suboptimality gap is basically g squared times t over 2. So it's made smaller as we take smaller and smaller steps. Here, the only difference I claim is really the 5, because we can think about this quantity, mg quantity squared. Mg is really the Lipschitz constant for our whole function. Okay, so if we have fi each being g Lipschitz, I equals 1 through m, then that implies that the sum of our functions fi is mg Lipschitz. Okay. So we think of this as the Lipschitz constant for the criterion, and what we get is a very similar suboptimality gap except for a 5. Okay, and just to be precise, for the randomized rule, this holds with probability 1, right? Because this is actually random, right? This guy. So this statement is true with probability 1 if we're selecting which function to use when we compute subgradients randomly at each iteration. Okay, and for diminishing step sizes, both rules satisfy, essentially the same result we had before, which is that we get in the limit the optimal criterion value, as long as you take, say, these tk's to be something like 1 over k. It's an example of something that would work. Again, this interpreted with probability 1 if you're talking about the randomized rule. So I would say, looking at this in terms of convergence behavior, right? If you don't think about rates in particular, just whether or not it converges and what the guaranteed suboptimality is, these stochastic rules look like they perform more or less the same as the usual batch subgradient method. Okay, so the results are very similar. Convergence rates is where things get, I think, kind of interesting and different, because we'll see that there is a big advantage in principle to using the randomized rule. So if we look back carefully, then it wasn't just 1 over epsilon squared that we derived as the rate for the subgradient method. It was 1 over the Lipschitz constant squared divided by epsilon squared. Okay, let's just go back to where we saw that. That came from the basic inequality, and we'd gone through this calculation last time. The number of iterations needed, for example, in order to get an epsilon suboptimal solution, we upper bounded by r squared times g squared over epsilon squared. R squared was the square distance between where we started an optima and an optimal solution. G was the Lipschitz constant for our criterion, and epsilon was the suboptimality gap that we wanted in the end. So treating this like a constant, it's really the Lipschitz constant squared over epsilon squared. Okay, so that's going to matter here for this comparison. So I'm citing here g squared batch. So think about this as the Lipschitz constant for the whole function. The cyclic rule, it turns out you can prove, has iteration complexity the number of iterations needed, each iteration just being one, calculating a subgradient for, let's say, one of these functions fi and moving in the direction opposite to that, m cubed times g squared over epsilon squared. Okay, this is how many iterations we need to get an epsilon suboptimal solution. Remember, g here was the Lipschitz constant that's just associated with one of these functions fi. So if I ask how many cycles are needed, right, one cycle being m iterations, then the answer is divide this by m, right? That's just a relationship between, there's m iterations in one cycle. And that's a fair thing to think about compared to the batch method, right? Because one full cycle of stochastic subgradient performs the same number of computations as one iteration of the batch method. Okay, so the number of cycles needed is on the order of m squared g squared over epsilon squared. So when we look at the cyclic rule, that seems comparable to the batch method, right? It's the Lipschitz constant squared for the whole criterion divided by epsilon squared. So looks maybe as if there's no real reason in terms of rate to use the cyclic rule. The randomized rule actually has, on paper, a much more favorable convergence rate. And this result is a result that holds an expectation. So to be precise, this is a bound on the expected number of iterations needed by the randomized rule, because it's random. So the iteration complexity turns out as m squared times g squared over epsilon squared, which is a factor of m faster, this average case rate, than the cyclic rule. Which means that if we want to ask how many cycles are needed in the randomized subgradient method in order to achieve an epsilon suboptimality bound, then the answer is m times g squared over epsilon squared. So it's a full factor of m faster than the batch method and then the cyclic method. Okay, so if m is very large, then the randomized rule on paper appears to have an enormous savings, right, over the batch method or the cyclic method. So it's a pretty convincing reason, I'd say, to use randomized stochastic methods when m is large, right, because we get an epsilon suboptimal solution with essentially m fewer computations, where m is the number of functions. And think about when this is used. This is usually used when this is a sum over functions, each function identifying a data point in our collection. So m would be the number of data points. So that if you have a lot of data points, then this is a very big difference between these rates. Now, maybe an important thing just to point out, though, is that I don't think this should not be damning for the cyclic rule. I don't think we're supposed to look at this and say the cyclic rule is definitively just much worse than the randomized rule. It's that this is a worst case bound. Right? The cyclic rule is just an algorithm that's deterministic. That's a worst case bound. This is an average case bound. So it's easier to analyze the randomized rule than the cyclic rule. I don't think, as far as I understand in practice, people really think that the cyclic rule performs poorly. It's just the usual comparison between deterministic and randomized methods. This can have maybe some pretty bad worst case behavior. This one is maybe somehow smoother or safer. It's easier to analyze, and we avoid worst case behavior in practice by using it. I know that there is quite a bit of interest currently in analyzing deterministic rules like the cyclic rule in this context and other contexts like coordinate descent, which we'll cover later in the course, to show they actually do have quite good behavior, although this is an older result that I'm citing, and it's really just that the average case analysis is amenable to do here for the randomized rule. Okay, so the paper that proves all this is listed in the references. It's a paper from a little while back. Okay, so that was it with rates. Let me just kind of put this in the context of an example before we finish off with subgradient method. Let's go back to the logistic regression problem, where suppose I'm trying to, fit a classifier to some labels yi, which are 0 or 1 for over a bunch of different instances or observations from predictors xi. Okay, this is the standard logistic regression problem. And now we're talking stochastic gradient descent because this is differentiable. But the rates for SGD are just exactly these as well. Okay, this applies to SGD. I mean, it kind of obviously applies to SGD because it applies to stochastic subgradient method, but they're no better for stochastic gradient method. These are what you'll see as well. Okay, when you're talking about stochastic methods, it turns out that smooth or non-smooth, this is the analysis. So let's suppose that we have huge number of points. Like keep in mind something so large that it's prohibitive just to do one full gradient computation, like in the hundreds of millions. Then we don't want to compute this full gradient, right? It's too expensive to compute this sum. So one batch update, right, is going to cost on the order of n times p computations, where n is the number of observations and p is the number of features. And one stochastic update only costs on the order of p computations, right? Because we're just evaluating one of these things, not a sum of any of these things. So if we're able to do something like n fewer cycles with stochastic gradient descent versus gradient descent, that's a very big deal for a problem when n is so large, right? Like in the hundreds of millions. Okay, so here's just an example I wanted to show of kind of the classic picture that you see when people discuss stochastic methods, which is that the stochastic methods they make progress very quickly early on, and so they appear to make progress even faster than the batch method at the start. But as you get closer to optima, the stochastic methods take a lot longer to converge, and in fact they won't converge if the step sizes are fixed, right? We know that we're just going to get something like this, right? We'll get something where we can converge up to some tolerance, but we won't necessarily converge to the optimal criterion value. Okay, so they just kind of bounce around the optima for a while. What people say, I guess if this is a logistic regression problem, right, where let's say n is huge, p is also big, is that, well, that's good enough, right? If you're close to the solution, then maybe statistically speaking, you have coefficients here, right, that enable you to predict y as a function of x to high enough accuracy, right? It's good enough. I don't really care that I'm actually solving this optimization problem to arbitrary number of digits of accuracy. I may be ending up with something that's kind of still useful for my original purposes. That's usually the kind of argument people use when they use subgradient methods, and these don't converge to really high accuracy. We will see a bit more on stochastic methods later in the course. I was planning on revisiting them at least when we kind of did a bunch of advanced topics, where we can see that there are some variants on the kind of classic stochastic methods like the ones we've talked about these last few lectures that actually do have guarantees about converging to high accuracy solutions. Okay, this is really recent stuff in the last maybe 2 or 3 years. So there are modifications you can make to stuff like SGD that, at least theoretically and in some experiments as well, give you much faster and much in convergence to much higher accuracy solutions. Although I think that in terms of whether they're as widespread in practice, I'd say that people are still kind of figuring that out. Question?
Do people ever in practice sort of run stochastic gradient descent for a while and then switch over, or is it that your step size still work better or other methods?
Yeah, it's a good question. I'm sure people do all sorts of things in practice that I'm not really aware of, or that are clever and probably work well in certain situations. So I think people do switch between algorithms. I don't know that in a lot of situations that makes sense when we talk about problems of this size, because then even one gradient computation is so much that it's probably not worth it. But there are probably hybrids. Like, for example, I guess I didn't mention this explicitly, although I should have. One very natural kind of middleman between stochastic, say, gradient descent and gradient descent is to do mini-batch. So instead of just taking one point, let's say I choose q points, where q is something that's much smaller than m. Then I can actually use the sum of those functions, the sum of their subgradients or gradients, right, to give the update direction, rather than the full sum, rather than just one. And so mini-batch methods kind of lay somewhere in the middle, and I think people do play with batch sizes all the time in order to get kind of convergence to higher accuracy solutions. And they may even change those dynamically. Good questions. Other questions? Okay. So I guess that'll finish our lecture on subgradient method. Just to reiterate this point before we move on to proximal gradient, the subgradient method is in a sense, optimal in terms of what it's doing over the class of convex Lipschitz functions. There's a theorem from Nesterov's monograph on convex optimization where he proves that this kind of rate, 1 over the square root of k, which is the same as 1 over epsilon squared, just in a little different notation, right, is a lower bound on any non-smooth first-order method. So any method that makes updates by combining subgradients of points that they've seen of the criterion at points that you've seen so far in linear combination and starting at some point x0. So the methods of this form are just kind of somehow fundamentally limited over the class of convex Lipschitz functions by this rate. Okay, we just can't do better than 1 over epsilon squared. So what we'll see just now is a proximal gradient method, which instead of trying to minimize arbitrary non-smooth convex functions, we think about minimizing convex functions that have a particular structure. So we're going to kind of restrict our attention a bit, okay, away from this very broad, very hard problem class to one in which we have a sum of 2 functions, say g and h, both being convex, this guy being smooth and possibly very complicated, but smooth, so differentiable, and this guy being non-smooth, which makes the entire criterion non-smooth, but being simple in the sense that something called its proximal operator is known. Okay, so we're going to think about sums of convex differentiable functions with convex non-differentiable but simple functions. It turns out that we're going to be able to write down a much more efficient algorithm than the subgradient method for this problem. Let's take a break. It seems like a good place to take a break, and then we'll come back and do a proximal gradient just in a minute. Proximal gradient, we will discuss its convergence behavior, although to analyze it, actually that's on your homework. You're going to be constructing the rate for proximal gradient on your homework. I think that's question 3. And then we'll talk about 2 applications of proximal gradient and 2 kind of very common problems. The first is the lasso, and the second is a trace norm regularized problem that's often used for matrix completion. Then we'll talk about some special cases of proximal gradient, and we'll see things like projected gradient coming out of it. And the very last bit we'll talk about is acceleration. So how do we get, if you recall back all the way to gradient descent, I'd claim that even gradient descent can be made faster, and that's through use of a technique called acceleration, which applies even more broadly to proximal gradient descent, and we'll study that as well. So the setup we're considering is we're considering functions of this form. Our criterion value is equal to the sum of 2 other functions, g plus h, where g is convex and smooth. We're going to assume it has a full domain, just for simplicity. And h is convex, but it's not necessarily smooth. Okay, so let's remember how we got, or one way that we saw to motivate the gradient descent updates. Let's remember that. If f were differentiable, then remember we would have, with gradient descent, we'd do something like this. Okay, we'd move in the direction of the negative gradient over and over again to get our next point, which I'm calling x plus. And how we motivated that one way was actually through a quadratic approximation to f around x, where we replaced the Hessian by just a scaled version of the identity. So that if we actually, instead of looking at f, if we looked at at the point x, say this is the point x, suppose we took a quadratic approximation like this guy, and we called that, I guess here I'm calling it f tilde t. It's the point x. Then we, instead of minimizing f, which is hard, we may think about minimizing f tilde t, which is easy because it's a quadratic, and that would actually just exactly give us this gradient update. Okay, so the definition for f tilde of t is here on the slide. It's just the usual second order expansion to our function f around the point x, but replacing the Hessian by 1 over t times the identity. That's one way to motivate gradient descent. Repeatedly forming a quadratic approximation, then minimizing that quadratic approximation in order to give you the next point. So because f is not smooth here, this kind of logic is not going to work, right? Because, for example, already the gradient is not defined for this function because h is not smooth. Okay, so one thing we could think about doing, rather than kind of falling back on subgradients like we did with the subgradient method, we could think about keeping something like this quadratic approximation, but only applying this to g, right? Because g is the smooth part. So why don't we replace g by its quadratic approximation? That's what we'll think about doing now. So make a quadratic approximation to g only. Leave h alone because it's not smooth, so we can't even talk about its gradient. And instead of minimizing f, which is g plus h, let's minimize g tilde of t plus h, where g tilde of t is the quadratic approximation to g around the point x. Okay, where we use, instead of the Hessian of g, we use 1 over t times identity. So if we didn't have a function h at all, this would be nothing more than doing the gradient update for g, right? Because this is exactly like what we saw with gradient descent. We have another function, so we're actually thinking about minimizing a sum of these two, quadratic approximation to g plus h. And this is just literally what we mean by that. This is the definition of g tilde of t. Right? It's the first order approximation plus 1 over 2t times the norm between z minus x squared plus h of z. Okay? And we can actually just rewrite this in a form that's more convenient. There's nothing really going on between steps that's sophisticated. Here I'm just writing this as the distance between, square distance between z and the gradient update to g times 1 over 2t. I'm collapsing all of these terms down into just this expression. Okay? It's because the minimizers of these two expressions are the same. They differ by constants, but the minimizers are the same. So to see that, just expand this expression. Okay, expand this. We get this squared times 1 over 2t, which is there. We get minus 2 times the inner product between this and this, which is exactly this term after we multiply by 1 over 2t in the front. And then we get a bunch of constant terms that don't depend on z. And that in those terms in this guy, for example, don't matter because we're talking about the minimum here over z. So all we've done is just rewritten this in a convenient form. So think about making the following update. Choosing our next point, x plus, to minimize over all candidate z, a quadratic approximation to g plus our original function h, which is the same as minimizing the sum of these two terms, 1 over 2t times the distance between the gradient update, the point that gradient descent would take us next if we had g alone, and z, and also h of z. So we can interpret these two terms as follows. We're trying to minimize the sum of these two terms. This one is trying to encourage us to stay close to what we would have gotten if we just took a gradient update with g alone, right? Because that's sensible if we're trying to minimize the sum of g plus h. And this one's also trying to make h small in the meantime. It's saying don't forget about h. And this parameter t, it kind of controls the relative importance of these two terms. Right? So if t is very small, then we're going to be placing a lot of importance on staying close to the gradient update for g. Right? Not much importance on minimizing h. If t is very large, then it's the opposite. This actually defines for us an algorithm called proximal descent. This itself is exactly what we're going to call proximal gradient descent. We're just going to introduce a bit of notation for what's called the proximal mapping so that we can write this a little bit more simply. So for any function h, we're going to define an associated mapping called the prox. Okay, and it's defined as follows. As a function of x, it's going to find for you the point z that minimizes this criterion. 1 over 2t times the norm of x minus z squared plus h of z. Okay, so it is defined as the minimizer of this criterion at the point x. And the sub t is just emphasizing the fact here that this actually depends on a parameter t, which kind of, like we said, weighs the importance of these two terms. It also depends on h. Okay, this proximal mapping depends on h. I've hidden that in the notation, but sometimes you'll see me writing prox subscript h comma t to emphasize that it depends on both h and t. So let's just pause for a second and convince ourselves this is actually a mapping. It's a well-defined function. So you give an x, it gives you back one thing. So why is that the case? This is defined as the solution to a minimization problem. Is this problem convex? What do you guys think about from what we've assumed so far? Is this problem convex? Yes. Does this problem have a unique solution? it does, right? Because it's strictly convex because of this term. So even if h was not strictly convex, the sum of this and h will be strictly convex because this is strictly convex, right? This is a quadratic. It's like z minus x squared. Okay, so this thing is strictly convex. So it's a strictly convex problem, which means it has a unique solution, and we're taking that unique solution as the prox. Okay, so it's really it's well defined. It's not like there can be more than one minimizers to this criterion. So proximal gradient descent, if we write it in the language, that uses this operator, it's defined as follows. At every step k, we make a gradient update according to the function g. So we take xk minus 1 minus the step size tk times grad of g at the point xk minus 1. So we kind of ignore h. And then we apply the prox operator for h. Okay, which means that we find the point z that minimizes essentially exactly this, right? The sum of these two terms. Because the prox operator is just defined as at x as the argument of this whole expression, we replace this by x, and we're just evaluating that at the gradient step for g. Okay, so it's just really the same logic as we saw in the last slide. Comes from the motivation of doing a quadratic expansion to g, adding h to that, and then minimizing their sum. So if you want to make this update step look more familiar, right, this doesn't quite look like what we do in gradient descent. It kind of does, but we have this outer call to a prox. You will often see this written as xk is equal to xk minus 1 minus tk times something called the generalized gradient, which we denote by capital G at the point xk minus 1, where this guy is just defined in such a way that it makes this relationship true, given that this is our actual algorithm. Okay, so there's nothing like insightful happening here. I'm just saying you can always define G in such a way that actually you can write the updates in this form. And you can treat this kind of like the gradient. We call it the generalized gradient. And in fact, it has a lot of properties of the gradient. And that's something that you'll leverage when you prove that proximal gradient converges on your homework. That this thing actually has a lot of properties that are similar to what we know about gradients for convex functions. Okay, so that's how it's defined. At a point x, it's just x minus the prox over t. Again, nothing super insightful. It's just a way that we can write this in a more familiar form. Okay. If you've seen this for the first time, you may may kind of balk and think this looks a bit silly, right? Because I've told you that we want to minimize a sum of s of g plus h. In order to do so, I'm going to repeatedly take steps of this form. Okay, this is easy to do, right? But then I'm telling you we have to evaluate this prox. And that prox is itself a minimization. So I've swapped out one minimization, which is the sum to minimize the sum of g plus h, with a bunch of minimizations over and over again. And that may look a little bit cheap, right? You can ask, how is that really any better? And the key point to keep in mind is that we only ever really run proximal gradient or talk about proximal gradient when this prox operator can be either computed analytically or can be computed very efficiently. So even though we have a sequence of minimizations to perform at each step, like of this form, argument of simple quadratic times 1 over 2t plus h of z, we only really think about applying this to functions h, applying proximal gradient descent when the non-smooth part h is simple enough that this thing has either an analytic form or it's efficiently computable. Okay, so some things to point out is that, as I've kind of already hinted, this proximal mapping does not depend on the function g at all. It's defined entirely in terms of h. So if h is something simple and g is horrendously complicated, then that doesn't really make these steps any more complicated as long as we can take the gradient of g efficiently. Okay, it's only changing h that makes the prox operator complicated. It's not really g that plays a role, and all we need from g is a notion of how to compute its gradients. And the convergence analysis that we're going to be describing and that you'll prove in the homework is going to be in terms of number of iterations of this algorithm. But keep in mind that each step actually evaluates the prox. Right? Each step is essentially a full solve of this inner minimization problem. And that can be expensive or that can be cheap. It really just depends on the problem. And in that sense, it's not always fair to compare this, say, to gradient descent, where the iterations don't really have that form, and one iteration here could be maybe much more expensive than an iteration of gradient descent. Okay, so keep in mind that when we say that this converges at a certain rate, that's the number of iterations, which is the number of prox evaluations that we're going to need. It's not like number of flops or something. Okay, we're not making comparisons at that level. Okay, I think it really helps to see an example. So let's just jump into the, let's say the lasso problem, to give an example of proximal gradient. And this is, I guess, our second algorithm for the lasso, because we could have applied subgradient method, but it's by far the most, out of subgradient versus proximal gradient, this is definitely the more efficient of the two. In general, and also especially for this problem. Okay, this is an algorithm that people actually, I wouldn't say it's the leading algorithm for the lasso, but it's certainly an algorithm that people would use and can use in practice. So to think about applying it to the lasso criterion, remember in this problem we have a kind of usual least squared error loss and a tuning parameter lambda times the L1 norm of beta. We want to minimize this over all over beta. We think about splitting up the criterion into a smooth part and a non-smooth but simplish part. Okay, that's this L1 norm. So that's our G of beta, that's our H of beta. And in order to run proximal gradient descent, we need two things. We need to know how to compute the gradient of G, and we need to know how to compute the prox operator of H. Okay, the gradient of G is very simple, and this should be something that you guys all can recite in your sleep at this point after we've seen this, several times. This is just going to be, x transpose x beta minus y. That's the gradient of this part. So that's down. But we need to know how to compute the prox operator of this part. Okay, and let's first think about how to compute the, let's just actually write it out. So the prox operator, right, is, by definition, it's the solution to the following problem. At the point beta, for example, we find the point z that minimizes 1 over 2t times the norm of beta minus z squared plus h of beta, and that's lambda times the L1 norm of z. Okay, that's the definition of the prox operator. Equivalently, I can actually write it like this, right? Prox of beta is equal to the argmin over all z of 1 over 2 times t times lambda beta minus z squared plus the L1 norm of z. Right, I've just multiplied or divided my criterion by lambda. That's not going to change the minimizer, right? So it's another way of defining the prox. If you recall what we proved when we talked about subgradients, we actually proved that the solution to this problem was soft thresholding. And it's soft thresholding at the level okay, I guess it's probably more clear to write it like this, actually. These are all equivalent, but to see that it's soft thresholding according to our lectures on subgradients, it's probably more clear to write it like this. So now I just multiplied the whole criterion by t lambda. All these forms are equivalent. So from what we saw on subgradients, this is nothing more we know than soft thresholding of beta. That's what the solution is. And it's at the level lambda, or t times lambda, right? Whatever, lambda times t. Because that's what's multiplying the L1 norm. So if you pass me in beta, then I look at each component, and I compare it in absolute value to lambda times t. If it's smaller than lambda times t in absolute value, then I set it equal to 0. If it's larger, then I subtract lambda t off of it, or I add lambda t to it, depending on whether it's larger than t or whether it's smaller than minus lambda t, right, depending on its sign. So that's exactly the soft thresholding operator. So I chose an example where we know the prox, because we actually computed that a few lectures ago. And this is very efficient, right? This is order p, right here, where p is the dimension of beta. I just go through the component and make very simple checks. That's it. So what does proximal gradient look like? We first take a gradient update according to G. And remember, the gradient I can write as minus x transpose y minus x beta here. So if I do beta minus t times the gradient, that's beta plus t times the inner products of x with the residual. plus t times x transpose y minus x beta, and I apply the prox to that. So I just take this quantity, and I either set it equal to 0 if it's too small an absolute value in any component, or I move it towards 0 by the amount lambda times t. Okay, that's all that proximal gradient is doing in this case. And we can also see now from the perspective of the algorithm, it's kind of neat, why we get sparsity in the lasso problem. Okay, we'll see that from the perspective of the, well, we actually saw that from the perspective of the subgradient optimality conditions for the lasso. But we can also see that algorithmically here, right? Why do we get sparsity at the solution? Well, one way is to say that look what proximal gradient is doing. Okay, we're going to assert that it converges in just a few slides, but if you believe that it converges for now, it's actually doing soft thresholding over and over again, right? And we know that soft thresholding can give us zeros, and it gives us more zeros if lambda is larger because it soft thresholds any component whose absolute value is less than lambda t. So this is often called ISTA, if you read about this in the literature. It was proposed by Beck and Tabou in 2008 when proximal gradient, I think, was kind of revived in some sense. Although proximal gradient itself is a much older algorithm, they applied this to a class of problems where you had something like a smooth function plus an L1 norm. And they called this the iterative soft thresholding algorithm, or ISTA. So here's an example of how it performs compared to subgradient method. And the comparison here, I claim, is actually really fair because each step of subgradient method and each step of proximal gradient are about the same computationally in terms of their expense. Okay, so I'll let you write out the steps for the subgradient method for the lasso. I can't remember if we've done that from last time, but as an exercise, you can try that. You can see that they're not any more expensive than this. But we get much faster convergence with proximal gradient. Okay? Just to emphasize as well, what happens if I change the loss here to logistic loss? So instead of solving the lasso, I'm solving logistic regression plus an L1 penalty. Or something else that's quite complicated but convex and smooth plus an L1 penalty. Well, that doesn't really change anything at all, right? As long as you can compute the gradient of the smooth part. Because our updates are now just this. They're take beta that you had before, subtract off t times the gradient of your smooth part at beta, then soft threshold that. That's all that proximal is going to be doing, proximal gradient is going to be doing when h is the L1 norm. So this is still an iterative soft thresholding algorithm. This is just dictated by the smooth part of the problem now. Okay, so for logistic regression, for example, you could plug in the gradient of the logistic loss to see what that looks like. It's going to be very similar, just replacing residuals here by y minus the predicted probabilities. Okay, so I guess we can state the convergence analysis, and then it looks like we're going to be out of time after that. So we're going to have a pretty similar setup when we talk about convergence that we have in previous lectures for gradient descent and whatnot. So f is going to be convex and differentiable with its gradient being a Lipschitz function with constant, let's say, L. And h, we're going to just simply state it as its prox can be evaluated. So it's convex and its prox can be evaluated. Because we're going to talk about iterations of proximal gradient, each iteration being one evaluation of this prox. So the analysis for proximal gradient is, it looks essentially the exact same as what we saw for gradient descent. If we have a fixed step size that's less than or equal to 1 over the Lipschitz constant, then after k iterations, the difference between f at xk and f star is less than or equal to how far we started in terms of our initial guess versus the solution squared divided by 2 times t times k. So we say that its convergence rate is 1 over epsilon, right? It's 1 over k in this notation, or if we want to set this equal to epsilon and solve for what k needs to be, it's still just 1 over epsilon. So it's the same as gradient descent, which seems great, but just a reminder that this counts the number of iterations, not the number of operations, right? If this prox operator happens to be expensive, then there could be a lot more going on per iteration here with proximal gradient. So I think we probably have time to squeeze in backtracking and its convergence rate. I don't know that we'll get to talk about much more than that. So let's just talk about essentially the same theorem, but for backtracking line search, and also what backtracking means for proximal gradient. So with gradient descent, we saw that we could choose the step sizes adaptively, which was quite helpful because typically we don't know the Lipschitz constant. So making a choice like this that guarantees convergence is not always possible in practice, or it's expensive to compute L. So backtracking not only tended to work very well in practice, but also kind of gave us this guaranteed convergence without needing to know the Lipschitz constant. There's a very similar notion that can be used for proximal gradient. And in fact, there are more than one ways to do backtracking. There's more than one way to do backtracking for proximal gradient descent. There's not just one way. And I chose a method that kind of operated entirely on G, because I thought it was kind of simple to remember. Let's recall the backtracking formulation for gradient descent. So backtracking for gradient descent, we're going to repeatedly check whether the following is true. If we're at, let's say the point x, and we're thinking about moving to this point, x minus t times the gradient of f, we're going to check whether or not this is true. It was alpha times t times the norm of the gradient squared divided by 2. Okay, something of that form. Well, in fact, we'll see if that was right or wrong, if I remember that wrong, just based on this. So, yeah, that I think is right. So it was alpha, let's just call it t over 2. It was actually alpha times t times the norm of the gradient of f squared. And I said that taking alpha to be equal to 1/2 was often kind of a simplifying choice. So this is what backtracking looks like for gradient descent. For proximal gradient, it's very similar, okay, except we're going to think about operating on G and not on H. We're going to try to get sufficient descent on G and not on G plus H. So in the usual backtracking, we check if this is true. If it is true, then we have to shrink t by a factor beta. If it's not true, then we've descended far enough and we actually make this update. So for proximal gradient, we check a similar criterion, but we actually replace, in a sense, grad f by the generalized gradient, because that's where we're going to be going next. These are the updates for proximal gradient, right? It's just the way to write them. And we recall that this came for actually like looking at a first order Taylor expansion of f, which puts us at something like this. So we want to make sure that we descend enough compared to a first order Taylor expansion after I've kind of changed the slope a bit. And this is what this looks like for proximal gradient. So what you can check is that if the generalized gradient happened to be equal to just the gradient of G, you get back this rule exactly. So this is really, in case that the generalized gradient was equal just to G, which means we just were doing gradient descent on G and there was no H at all, this is nothing more than what we saw as backtracking for gradient descent. But in general, this is how we think about backtracking when we have another function H in our criterion, so the generalized gradient has been changed, right? Now it's dictated by the prox operator rather than just by the gradient of G. So this is what it looks like for prox grad. Okay, this one's rather simple. You can also formulate versions that try to make sure that the descent on G plus H is kind of large enough. But I think this one works just fine. So under the same assumptions that we had kind of on this slide, backtracking line search with proximal gradient descent has the same convergence rate. It's really the same as what we saw for gradient descent. It's just still a 1 over epsilon rate, and we don't need to know the Lipschitz constant. Maybe the last thing to point out before we quit for the day is that there is something a bit subtle happening here in terms of computation. If this is true, then we're going to shrink t to be beta times t, right? Like, for example, 0.9 times t. And if it's false, then we're going to take x plus to be x minus t times the generalized gradient, right? Which is, as we know, it's just the prox. definition of proximal gradients updates. So why is this a bit subtle? Because if we don't have enough of a descent here, right, then we're going to be doing as usual in backtracking a shrinkage on the step size t. So we're going to take t to be something a bit smaller. But the next time we go and check this now, look what we're required to check. We're required to check whether x minus t times the generalized gradient at t is bigger than or equal to this side, this right-hand side. We're going to have to actually recompute the generalized gradient and add it at the new value of t, at the value of t that was smaller, right? Shrink and then check again. And this generalized gradient, remember, it's just kind of notationally convenient, but it means evaluating the proximal operator. So that means that in every inner loop of proximal gradient descent with backtracking line search, even in the backtracking inner loops, we have to evaluate the prox. So if the prox is expensive, backtracking can be very expensive, especially if, let's say, beta is taken to be something very large, like 0.99. So there's many, inner loops. There's many iterations in the inner loop. So just be aware of that. And I'll kind of emphasize that once again next time. But the prox operator is kind of sneaking in here with the generalized gradient. OK, that was all our time, and I'll see you guys on Wednesday.